In a quiet lab, a silver cylinder exhales cold like winter breathing. Across town, a fiber spool glows under a technician's lamp. On a bench top, a chip the size of a thumbnail wears a crown of microwave lines. These aren't props for a magic trick. They're the tools of a new craft, using superposition on purpose. If nature keeps options open, engineers have learned to guide those options, cancel the wrong ones, amplify the right ones, and turn quantum maybes into useful work. A classical computer checks possibilities one after another, patient, tireless, but ultimately single file. A quantum computer sets many routes in motion at once, then choreographs them so bad answers cancel while good answers add together. Think of a maze scene from above. Instead of trying every corridor, we let ripples explore the whole layout. Where ripples meet out of step, the path dims. Where they meet in step, it shines. This is more than a party trick. Search problems become leaner. Certain chemistry tasks, finding the most stable arrangement of electrons in a catalyst, say turn from impossible to plausible. Optimization landscapes that look like mountain ranges under fog suddenly reveal passes you couldn't see before. But there's a catch. Superpositions are skittish. A nudge from the outside world can make delicate drafts collapse too soon. So quantum engineers use error correction, spreading one logical bit of information across many physical qubits. In superconducting devices, they even store a bit in two opposite states of light at once, the so-called cat codes, so that a small disturbance doesn't ruin the message. None of this is free. One sturdy, reliable qubit can demand a crowd of helpers. Where does that leave us? Early processors are already useful as co-pilots. Specialists that hand classical computers better guesses for chemistry, materials, and optimization. The moonshot, general-purpose, and fault-tolerant machines will take time, patience, and thousands upon thousands of well-behaved qubits. The promise is real, the road is long. Some quantum problems are so tangled that equations alone give up. The workaround is wonderfully literal. Build a tiny, controllable stand-in, trap ions in neat rows, and make them push and pull like electrons in a crystal. Cool atoms into a calm, laser-made egg crate, and watch them act out the drama of magnetism or superconductivity. Use a programmable photonic circuit to mimic how light and matter flirt inside a solar cell. Rather than brute forcing a solution, we grow the equation and observe the answer. The payoff is practical. Better battery chemistries, cleaner catalysts for green fuels, hints for high-temperature superconductors. Sometimes a model universe is clearer than the math that describes it. When you tame quantum noise, the world whispers secrets. Atom interferometers split a cloud of ultra-cold atoms into two paths and reunite them. A tiny difference in the journey. Gravity a shade stronger here than there shows up as a telltale shift. With these instruments, scientists map hidden caverns, trace water tables under farmland, and listen for the swell and settle of magma beneath volcanoes. Inside a sliver of diamond, NV centers, which are flaws just a few atoms wide, behave like nanoscale compasses. They can read magnetic fields cell by cell, peeking into new materials and even sensing the blush of currents in living tissue. And then there are optical lattice clocks. Imagine an orchestra of identical atoms, each keeping time with a note so pure it drifts a second only over the span of the universe. These clocks promise sturdier GPS, better tests of whether nature's constants really stay constant, and ways to sense tiny changes in Earth's gravitational field, say, as groundwater moves. Even light's own hiss can be shaped. With squeezed light, we quiet the kind of fluctuation that matters and allow its partner to jitter more. This trade lets instruments hear fainter signals than classical physics would permit. The difference between missing a whisper and catching it clearly. Imagine sending a stream of single photons, each set in a particular orientation, as if tiny arrows were flying down a fiber. If no one meddles, those orientations arrive as sent. But if an eavesdropper even looks, the act of looking disturbs them. Errors spike, to throw away the key and try again. That is the heart of quantum key distribution. Secrecy guaranteed not by clever math, but by nature's rules. To go long distance, we link short, secure hops into a chain. Quantum repeaters use memories that hold fragile links until the next segment is ready, then stitch them together, entanglement passed hand to hand across a continent. These networks don't beam cat videos faster than light, they do something quieter and more profound. They make tampering obvious. Sometimes you can reveal an object with less light, not more. Send paired beams. One touches the scene, the other stays home. Compare them, and a picture emerges from noise ghost imaging with barely any illumination. In murky water, in smoky air, or over fragile paintings that shouldn't be bathed in brightness, correlation beats brute force. Likewise, using entangled or squeezed light can push imaging beyond classical limits, sharpening edges and reducing the grain in low-dose scans. When photons travel in company, their story carries extra detail. Long before dilution, fridges, and clean rooms, life learned to borrow quantum shortcuts. In photosynthesis, tiny packets of energy fan out through a protein maze, as if testing many routes at once. Subtle interference helps funnel that cargo to the reaction center with remarkable efficiency. Sunlight turned into chemistry with almost no waste. Migratory birds may carry entangled electron pairs and light-sensitive proteins called cryptochromes. Earth's weak magnetic field tilts this delicate balance. The chemistry downstream changes. The bird perceives a faint directional cue, a map written in twilight. And in enzymes, tunneling lets protons or electrons slip through energy barriers rather than climbing over them, speeding reactions at body temperature. Not every proposal survives testing, and debate is healthy. But the pattern is clear. When energy is scarce and timing matters, evolution favors quantum economy. It's tempting to imagine a universal quantum boost, a silver bullet for every hard problem. Nature is stricter than that. Quantum algorithms help where interference can be engineered to cancel the wrong answers. Many tasks simply don't fit that mold. Scaling is hard. Single, reliable, logical qubit can demand dozens or hundreds of physical ones. Keeping thousands in step while guarding them from the noisy world is an immense engineering challenge. Progress is steady, not meteoric. On security, the sky isn't falling, but the horizon is moving. Some of today's public key cryptography will be vulnerable to future quantum attack. The remedy is already known: post-quantum classical algorithms that resist both kinds of computers. For secrets that must last decades, the time to migrate is now. There's also cost and conscience. Big machines mean cryogens, clean rooms, and careful supply chains. As nations invest, we should ask who benefits, how widely training and access are shared, and how to minimize environmental impact. Responsible storytelling matters too. Quantum miracle headlines may harvest clicks, but they plant confusion. Let's celebrate real benchmarks, admit uncertainty, and be honest about timelines. Wonder does not need exaggeration. If superposition can root a maze and measure a mountain's hollows, why doesn't your coffee mug blur across the table? Because the world is a relentless observer. Air molecules, stray light, the table itself, each steals a hint of the mug's state, shredding the delicate phases that make interference possible. Engineers fight this decoherence by carving tiny sanctuaries, brief shelters where quantum drafts can work before the curtain falls. And yet, even inside that curtain, the lesson is generous. We live among many maybes, most of them hidden, some of them harnessed, and build our lives from the few that harden into facts. In the final act, we'll gather the threads. What the cat taught us, what superposition means for meaning itself, and how to carry a little quantum humility into a classical world.